In this video, I'm going to talk about how a compiler actually generates code from an expression that's being tested in an if statement, because this is the background for one of the activities about the optimizer that's going to use regular expressions and some file I/O. So that's the kind of the background of what's going on here. Do you absolutely need this information? Well, no, not really, but it's kind of good to know what you're doing. So imagine that we had an expression like this. We had if score plus 10 is less than 100. This is some totally arbitrary thing that I just kind of mocked up. What does the compiler turn this thing into so it can generate code from it? Well, it's going to turn this score plus 10 less than 100 into an expression tree, or into a tree-like structure. And we're going to traverse that tree-like structure, and in conjunction with another data structure where we're going to store values. And that other data structure is the stack. And the stack is just like Squidward here. It is a data structure where you put stuff in and you take stuff out. So the first thing in is the last thing out. Things go in the top of the stack and they come out the top of the stack. So first in, last out. Now just bear with me here. Let's take a look at what this expression here, the score plus 10 less than 100, is going to look like as a tree. It's going to look something like this, where the operators are the interior nodes and any value is a leaf node on the tree. And what we can do is evaluate this recursively. So to evaluate this less than sign, we'd say, okay, evaluate the left and put it somewhere, evaluate the right, put that somewhere, and then take those two things and perform the less than operation. And that somewhere where we're going to put the temporary results is the stack. It's Squidward. It's our Pez dispenser where we're going to put data in and take data out, or more technically, we're going to push data in and pop data out. Now let's talk about the exact algorithm for this. So we're going to do a depth first search, or depth first traversal of this tree. We're going to go down the left side, down the right side, then we're going to apply the operator. So we're going to write the code to push the left side onto the stack. We're going to write the code to push the right side onto the stack. And then we're going to pop those two values out of the stack and perform that operation. So if we're evaluating this node here, the less than, by the time it pops its values out, it's going to have score plus 10 computed in the stack, and it's going to have the 100 computed in the stack. So let's just sort of write that process out just a little more formally. So we'll write an algorithm here. So recursively, we're going to visit the tree. And if the node we're visiting is a leaf, we're going to get the value and push that onto the stack. So if it's a variable, we just read that variable, push it onto the stack. Maybe if it's the return result of a function call, we make the function call and we push the result onto the stack. If the node that we're visiting is not a leaf node, then we're going to visit the left side, visit the right side, and then pop the two values out of the stack and apply the operator to get a result, and then we put the result back in the stack for the next operator up to find. So let's just walk through how that would work. So imagine that we're trying to turn this. We've got this as a tree structure, and we're going to visit it and write out the code that corresponds to this expression tree. What's that going to look like? Well, we say, okay, visit a node. Is it a leaf? No. So visit the left, and then when we're all done with that, we're going to visit the right. So we visit the left. Is this a leaf node? Nope. So we visit the left, and then we're going to visit the right. So let's visit the left. Now we come down to score. Is that a leaf node? Yup. So we're going to put score, we're going to push score into our stack. So this is going to be our stack right here, our Squidward, our Pez dispenser. So we push score into the stack, and now we're done. So the recursion returns, and now we visit the right side of this subtree, and we say, okay, is this 10 a leaf node? Yep, that 10 is a leaf node, so we're going to push that into the stack. So now our stack contains the left side and the right side of that expression tree. So now this node has got its left side and its right side computed. We just need to pop them out of the stack, add them together, and then put the result back in the stack. So let's take a look at that. So we pop out score, or actually we pop out the 10 first, because that's on the top of the stack. That's going to go in maybe a temporary variable. We pop out score into a register, like the accumulator, AF or A whatever it is in Z or x86 land. I'm a Z80 guy. Then we'll compare those. So we'll pop 10 into a temporary variable, pop score into the accumulator, and then compare that accumulator register with our variable and push the result back in the stack. So we're going to pop out the 10, pop out score, and we're going to push back in the results. We'll have 10 plus score. Okay, awesome. So now we're kind of done with this subtree right here, and the recursion comes back. We look at this node. Okay, we visited the left side. Now we have to visit the right side. Okay, so this is, what do we have on the right side? We have a constant. That's 100. So is that a leaf node? Yep. So push it into the stack. There we go. And now there's nothing more to do. The recursion returns. And finally, we're back at our less than operator. And we just keep repeating the pattern. So what do? We pop out the right side into a temporary variable. We pop out the left side into the accumulator register, and then we compare and push the result back in the stack. So let's look at that. So we're going to pop out the 100, and we're going to pop out, we're going to pop out the 100. We're going to pop out 10 plus score into the accumulator, and let's just assume that evaluates to true or 1. So we'll push a true or a 1 back into the stack, and there's our final result. So now the last thing we need to do is just pop this out and compare it to 0. If the result is false, then we would jump into the code that represents the body of the if statement. Now, I just misspoke. So if this is true, if we compare this to true, if this is true, if true is true, then we jump into the code. Or you could say, where I was going with that was, if it's false, then you jump over the body of the if statement. That's actually how it really works under the hood. There's no concept of if this is true, jump here. If it's not true, skip the body of the if statement. So that's kind of conceptually what's going on. So the whole result is that we've traversed that tree to generate the code that's going to evaluate our variables and constants and push into the stack the result that we want. So let's take a quick look at like some pseudocode that might actually generate. This is kind of a mishmash of English, pseudocode and kind of Z80 assembly. So remember, we visit the left side. Then we visit the left side. Okay, that's a leaf node. He'll push the score into the stack, return, and then traverse the right side. Okay, so that's a constant 10. Push the 10 into the stack, then pop the 10 out into a temporary variable, pop the stack, which would be our score, into the accumulator, add them together, push the result back in the stack. So now we have score plus 10. And then we're done on this side, so we return, and now we visit the right side of the less than, and that would be push 100 into the stack and return. Okay, so now that we've returned, we've evaluated the left, we've evaluated the right. What do? We pop the right into a temporary variable, pop the left into the accumulator, perform the comparison, and push the result into the stack. Then finally, we pop the result out of the stack and compare it to 0 or true, or however we're going to implement our if statements. Usually we say if it's false, skip over it. So if you wrote if something is true, what that gets turned into is if it's false, skip over it. All right, so now there's some things to take a note here, is that there's a lot of inefficiencies going on here, right? So I'm going to load the score, I'm going to push the score, and then I'm going to pop the score. So this push and this pop, they just undid each other. I pushed something into the spit, I just took it right back out. Like that's a waste, right? I could have just like left the score where it was. And the same thing here, right? I load 100 into a register, and then I push it into the stack, and I pop it right back out. So this push 100 and pop 100, this push 10 and pop 10, those just undo each other. They're just useless operations that, they're slow, because anytime you hit the stack, you've got to go out to memory as opposed to staying within the CPU. And you've also, you've added some extra instructions that you don't need, and you've also added a few bytes to your code. And that's not good. So the solution then is to write a program or a function that can go through your code and find these useless operations. That can I find a push and pop that undo each other and just remove them? Or if there's a push from into the stack and a pop into a different register, then you could just replace that with one move instruction. So that's what is going on here. We're going to run through our code, and we're going to write a program. We can turn this into an array of lines, an array of strings, and we can say, okay, is string I, does string I push something into register AF or something, or register BC into the stack? Okay, it does. All right, well, then is the next thing a pop? Okay, good. We can get rid of those, right? So here's kind of like what that would look like as assembly. So you can see load BC with score, push BC, load BC 10, push BC, pop BC. So this push and pop, they undo each other, right? So we don't need those. We can just get rid of both those lines. Same thing here with this push BC, pop BC, right? Because we just don't need them. Those operations are useless and they undo each other. So the tree traversal will generate code that is not necessarily very efficient, but it also generates inefficient code that's easy to optimize, because we can just use C# to read in the source file, turn the whole thing into an array of strings, scan through those strings, and look for operations that we know we can eliminate or shrink. So that's what this whole exercise is about. It's kind of like writing an optimizer for a compiler. Now, if you're asking, like, why would I ever do this? Well, I'll explain. So here's the website for the the adventure game development system that I've written, and I've been working with a guy in England, and he thinks that this thing is really cool and likes writing games with it. But the problem we keep bumping up into, or we were bumping up into, is the code size. Because what he's trying to do is get his games into a Sinclair Spectrum, which only has 48 kilobytes of contiguous RAM and no file system where you can page stuff out to. So the code has got to be really, really tight. It's got to be very compact. So I was looking at the code that the system outputs, the assembly language code, and I looked in there and I realized, oh, there's all these pushes and pops that undo each other, and we can fix. So the solution was to write a function to optimize the code. This function can read you give it a file name, it reads in the file, and it scans through, and it breaks the file up into an array of lines, and it says, okay, can I find two subsequent operations that just undo each other and I can just remove? And that's what it does. So it reads in the list of, it reads in the file as an array of lines, it converts that array of lines to a list, and then it scans through the list, and if it can find two operations that undo each other, it just deletes both of those lines from the list and then just keeps trucking along. And it turned out we were actually able to optimize out 386 bytes of code, which was enough to squeak this thing into the memory of a Sinclair Spectrum, which was super cool. So that was the context for this, right? So this tool writes out assembly language that using that algorithm I just showed you. That assembly language is not particularly efficient because of all the extra pushes and pops, but no problem. You just write a second pass function that reads the file and just cleans it up and gets rid of all the unneeded operations. So that is so that's what's going on in the optimizer program, and that is everything is very well explained in there. You're not going to have to know any assembly language. It's going to be really bulletproof what you need to do. So we're going to be using file.read all lines and file.write all lines. We're going to be using StreamWriter and to write out a log file. And we're going to be using the using statement to make sure that that file, that StreamWriter that's going to write out the log file, gets closed. And that's it. So this is a really good chance to work with those functions that convert between lists and arrays, to use the using statement to see what's in the file class. There's the read all lines, which and write all lines. Those are really useful. And then also the file.create and the StreamWriter. So all good, useful stuff. So, but if you have any questions on the instructions, just email me, and I will be happy to explain them further.